We got an early stream tonight. Early. Stream tonight. Organic chemistry. I post all these videos on my teacher site, so no big deal. If you can't tune in live, you know the deal. Alright, let's get going here. Alright, so tonight we are reviewing organic chemistry. We are really close to the end. We got 2 more of these left. So we are like midway through 4th quarter right now with the units that we're on. Last night was acids and bases. Sunday night was kinetics and equilibrium. And now we are on organic. So let's get started here. So the basic principles of organic chemistry is organic chemistry is the chemistry of carbon. Chemistry of carbon. So it's all about carbon. Carbon, 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 carbon. You see organic, you think carbon. So organic chemistry is all about carbon. Carbon, not any other element, just carbon. So we are mainly going to be dealing with table P, table Q, and table R. And then we'll go over isomers, we'll go over organic reactions, and then that's it. So table Q are basic hydrocarbons. So what is a hydrocarbon? A hydrocarbon is any organic compound. 2 R's there, Mr. G. Is any organic compound that contains hydrogens and carbons. And that's it. Just hydrogens and carbons. They can be saturated hydrocarbons, which means it's all single bonds. More specifically, all carbon-carbon bonds are single, because hydrogen can only have single bonds anyway. Or they can be unsaturated, which means the compound has a carbon-carbon double bond or a carbon-carbon triple bond. So unsaturated means you contain a double or triple bond, and saturated means you contain all single bonds. When you're drawing hydrocarbons, it's important to keep in mind that carbon wants 4 bonds always. Hydrogen wants 1 bond always. So carbon, no matter what, will always have 4 bonds in some way, shape, or form attached to it. Hydrogen, no matter what, will always have 1 bond in some way, shape, or form attached to it. It can only be a single bond, so it's pretty straightforward. So, when you look at table Q, there are alkanes. And alkanes are all carbon-carbon single bonds. They have the generic formula CnH2n plus 2. What does that mean? That means for every carbon, you multiply it by 2 and then add 2. So, if there's 2 carbons and you have an alkane, it's C2H6. If there's 3 carbons, multiply it by 2 and then add 2. If there's 4 carbons, multiply it by 2 and then add 2. So in addition to being able to look at a picture and identify if the carbon compound is saturated or unsaturated, you also need to be able to look at these formulas and identify if a carbon compound is saturated or unsaturated. And to do that, you kind of have to work backwards. But let's go over all the alkanes, all the ones in this reference table that are part of what they call the homologous series. So you see this word homologous or homologous series, you go to table Q. So next is an alkene. An alkene has a carbon-carbon double bond, and it has the generic formula of CnH2n. So if you have an alkene, for every 2 carbons, multiply it by 2, there's 4 hydrogens. If there are 3 carbons, multiply it by 2, 6 hydrogens. If there's 4 carbons, multiply it by 2, 8 hydrogens, etc., etc. The last one in that homologous series is called an alkyne. And an alkyne has a carbon-carbon triple bond. They have the generic formula of HNH2n minus 2. Sorry, CnH2n minus 2. So if there were 2 carbons, 2 times 2 is 4, minus 2 would be 2. 3 carbons, 3 times 2 is 6, minus 2 would be 4. If there were 4 carbons, 2 times 4 is 8, minus 2 would be 6. So in addition to looking at these pictures and identifying if the carbon-carbon bond is saturated or unsaturated, you also need to be able to look at a formula and determine if the carbon-carbon bond is saturated or unsaturated. So, how do you do this? Sorry, I just got a message from a kid. Just reading my reminds. How do you do this? Let's say you had a list of carbon compounds. C5H10, C6H10, C7H16, or C8H16. You would need to be able to identify if this is an alkane, alkene, or alkyne. So, in each formula, multiply the carbons times 2. If the carbons times 2 directly gives you the hydrogens, that's an alkene. If you have to do C times 2 minus 2 to get the hydrogens, that's an alkyne. These are always unsaturated. If you have to do C times 2 and then add 2 to get the hydrogens, you have an alkane and you are saturated. Again, you don't need to memorize these formulas. These general formulas are provided for you on table Q. So you have alkanes, alkenes, and alkynes. And it even says on the bottom, N is the number of carbon atoms. So, let's apply these formulas to each one. 5 times 2 is 10. The times 2 equals the hydrogens. This is an alkene, which means it's unsaturated. Next one. 6 times 2 is 12. 12 minus 2 is 10. That fits the formula for an alkyne, and that is unsaturated. 7 times 2 is 14. 14 plus 2 is 16. This is an alkane. This compound is saturated. 8 times 2 is 18. That's an alkene. Alkenes are unsaturated. So, that's the basics behind alkanes, alkenes, and alkynes. Let me fix that N. That looks weird. N. Alright? You also need to be able to draw carbon compounds. So, let's say you were given, and name. Let's say you were given C8H16. First, draw your carbons. C, 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 then boom. One more. Boom. Then, it says it needs 16 hydrogens. So 8 times 2 is 16. So this is an alkene, which means we need to put a double bond somewhere. And since it doesn't specify in a formula, we can just put it on the first one. Now be careful. You got to remember every carbon wants 4 bonds. I'm not going to draw the H's. All the remaining lines will be implied that there's an H. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Mr. G, why isn't there an H here or an H there? Well, 1, there's only 16 H's in this formula, but how did I know to only put 1 on this carbon? Well, count your bonds. We have 1, 2, 3, 4. So you can't fit another bond on that carbon. Same with the carbon to the left. We have 1, 2, 3, 4. Carbon only wants 4 bonds. How do we name this? Well, we need to look up what the prefix for 8 carbons is. And if I look on the reference table, 8 carbons is oct. And if it's an alkene, the ending is -ene. So we have, what's this compound? Oct for the 8 carbons, and then -ene because there's a double bond. Now, what if the question asked you to draw 4-octene? What does this 4 mean? So let's draw oct. 1, 2, 3, 4, 5, 6, 7, 8. You want to put the double bond on the first carbon, but this 4 tells you to put it after the 4th carbon. So count 4 carbons. 1, 2, 3, 4. And then after the 4th one, put the double bond. Fill in the rest with your hydrogens. And now you have 4-octene. Mr. G, what if the question asked you to draw 3-methyl pentane? Or let's do, would pentane work? Yeah, pentane. What does this mean? What does this mean? And what does that mean? So when you're drawing compounds, you need to work backwards. Let's look up what pent means. Pent means 5. So the number of carbon atoms in this formula is 5. Ane means we have an alkane, which means all of our carbon-carbon bonds are single bonds. So let's draw pentane. 1, 2, 3, 4, 5. Pentane. What does methyl mean? When you see this YL ending, that means we have a carbon compound or a carbon atom that's outside of our longest chain of carbons. So our longest chain of carbons in this formula is pentane. So our longest chain in a row is 1, 2, 3, 4, 5. So on carbon 3, there is a methyl sticking off of it. Well, what does methyl mean? According to the reference table, meth means 1 carbon atom. So on carbon number 3, I'm going to stick a carbon atom off of it. Carbon wants 4 bonds. Make sure you fill in the rest, and remember these are hydrogens, with your hydrogens. These are all hydrogens around. That is 3-methyl pentane. What if they gave you a drawing and you had to name it? So I always recommend to count your carbons and see what your longest chain is. Start at any of the extremes. So I'm going to start here. 1, 2, 3, 4, 5, 6. Okay, that chain's 7. Let's see if we can find a longer one. 1, 2, 3, 4, 5, 6, 7 again. What if I went to the right? 4, 5. Nope, that's not longer than 7. So our longest chain is in a row is 7 carbons. Box that chain in. Name the box. So we said there were 7 carbons in there. Go to your reference table. Look up what 7 means. 7 means hept. I see all single bonds in those carbons, so the ending is ane. Now, when you count carbons, you can go left to right or right to left. How do you know which way to count? You want to make sure those carbons outside of that box are on the smallest number possible. So you could count 1, 2, 3, 4, 5, 6, 7, and then they would be on carbon 5. But what if you count this way? 1, 2, 3. So if you count backwards, those carbons end up on carbon number 3. So we know that this is going to be 3 something heptane. How many carbons are outside the box? Well, there's 2 of them, and they're connected. And when 2 carbon atoms are connected, we say that group is eth-il with a YL. So we have 3-ethyl heptane. I'm going to draw this again slightly different. I'm going to draw my 7 carbons, and I'm going to put a carbon here and a carbon there. I'm going to draw my 4 bonds on each carbon. I'm going to box my longest chain. I'm going to name my longest chain. 1, 2, 3, 4, 5, 6, 7. That's heptane. I'm going to number my carbons in the smallest way possible that gets that side group on the smallest number possible. 1, 2, something heptane. What's the difference between that one? Well, first, I put it on a different numbered carbon, which is fine. But what else did I do? I took that carbon-carbon double bond, not double bond, but this carbon-carbon bond right here, and I broke it and put the other carbon on top. So instead of this being 2-ethyl heptane, I now have 1 carbon group by itself. That's a methyl. I have another carbon group by itself. That's again methyl. So this compound we would name 2,2 dimethyl heptane. How do you know to do that? Well, if you have 2 separate non-bonded carbons in any amount of groups, there could be 3 of them connected on various sides, but if you have 2 separate carbons that are not connected together anywhere outside of your box, you have to tell me where both of those carbons are. And in this one, both of those carbons are on the box chain number 2. They're both methyls, so we say dimethyl heptane. If I took this carbon and put it on that carbon instead of this being 2,2 dimethyl heptane, this would be, there's 1 on carbon 2, 2, 3 dimethyl heptane. Because I have one carbon outside box on number 2, and I have a second carbon outside my box on number 3. So, normally, when I count all my carbons, I see 9 carbons, right? There's 1, 2, 3, 4, 5, 6, 7 in my box, and then 8, 9 outside my box. And usually, when you have all single bonds, usually C9H20, that's a big 0, you would call nonane. But when I draw it differently and give it a different name, but keep the amount of carbons and hydrogens the same, you have what's called an isomer. So this is an isomer of nonane. This is an isomer of nonane. So an isomer means same formula, different structure, different properties. I have a feeling this is going to have to get broken up into 2 videos, but we'll see, because I have to do tomorrow. We'll see. So same formula, different structure, therefore different properties. And what do I mean by different properties? And what do I mean by the same formula? So let's say you had C5H12. C5 means you have pent. So this is pentane. And let's say the question was to draw an isomer of pentane. So an isomer needs to make sure that these numbers are the same, but that this looks so different that you can't call it pentane. You have to name it differently. What not to do? If you're asked to draw an isomer and you take that first carbon and you just stick it pointing up, that's still pentane, because in this structure, my longest chain is still 1, 2, 3, 4, 5. And then in this structure, well, my longest chain is still 1, 2, 3, 4, 5. To make an isomer, you have to break a bond and move that bond somewhere else. So an isomer of pentane could be take these 4 carbons, well, let me draw them all, and take this one and move it here instead. So now our longest chain is no longer 5. Our longest chain is 4. 1, 2, 3, 4. 4 is bute, like butane. So when you name this, you would say we have butane, and we have 1 carbon sticking out on number 2 in the box. This is 2-methyl butane. So when you draw isomers, you need to make sure that you don't do this. This is bad. No. You need to actually break a bond off of pentane and put that carbon somewhere that's not on one of the edges, or else that's just like taking a piece of paper. Oh, look, it's some geometry stuff. Taking a piece of paper and saying, that's not a piece of paper anymore. That's not one piece of paper. No, all you did was fold it up. That's the same thing. You didn't do anything. Or like some of my students said on a quiz, this is a stylus, but if I flip it this way, it's not a stylus anymore. Well, yes it is. So you can't just flip things around. You actually have to break a bond and then reattach it somewhere different that's not on the first carbon. Let's talk about table R. So table R is a table of your organic functional groups, aka what that means is you no longer have hydrocarbons. Let me change the size of my marker here. So everything on table R are not hydrocarbons because guess what? There's another element involved that's not hydrogen or carbon. So what is this showing you? If you have a halide, that means you have one of these groups attached to it. I'm not a big fan of the general formula. I don't like to talk about these. So I usually just cross this out because I think it's easier to see from just the examples they give you and from the item to the left there. I think this is much easier to see than this. So I'm not a big fan of that. But if you have a halide, that means at basic level you need to be able to recognize these. This is definitely going to be 2 videos because I want to do a bunch of practice with this. So you need to recognize that you have one of these functional groups attached, an F, a Cl, a Br, or an I, because those are all in group 17, and group 17 elements are called the halogens. And this is an example. So if you have a chlorine attached in your compound somewhere, you have a halide. When you go to name it, you name the carbon compound normally, and you tell them where is that halogen attached. Since that Cl is attached to carbon number 2 here, we say this is 2-chloropropane. So for example, if you had 3-bromopentane, you do this the same way you did before, but instead of putting a carbon compound on number 3, you're putting a bromine on number 3. So draw a pentane. On number 3, put a Br, and you fill in the rest normally. So it's the same rules as before, except now you have to pay attention to what your functional group is. Alcohol. An alcohol has an OH attached somewhere in that compound. When you go to name it, you have to change the ending to "all" for alcohol. This number tells me where is that OH. Is it on the first carbon, the second, the third, etc.? So for example, if it was asking you to draw, let's say, 2-butanol, that OL tells you we have an alcohol, which means we have an OH somewhere. So you basically just take butane, drop the E, and add OL. So I'm going to draw butane normally with my 4 carbons because but from table P means 4. On the second carbon, since this is butanol, there must be an OH attached to it. Fill in the rest normally. All of these will be hydrogens. So that's 2-butanol. Next, we have an ether. An ether has an oxygen sandwiched between 2 carbons. So this oxygen is always going to be sandwiched between 2 carbons. Now, when you're asked to name these things from a condensed formula, aka looking like this is condensed. You took this bonded compound and drew it without the bonds, basically. You need to draw these out to make sure you're doing it right. And I'll tell you what I mean when I get after aldehyde. So when you name ethers, you say this group first, 1 carbon, methyl, Look after the oxygen. There's 2 carbons here. That's an ethyl. And then just write the word ether at the end. So, if you were given, let's say CH3, CH2O, CH2, CH2, CH3. Right, 1, 2. How do you name this? 2 carbons, ethyl. 3 carbons, propyl. Ether, because there's an oxygen in the middle. Ethyl propyl ether. Now some of you are saying, wait, doesn't this oxygen here, isn't it bonded to this hydrogen? And then the oxygen over here is bonded to that carbon? To which I would say, draw this out. So, first was CH3. There's a C. Let me get more room. There's a C with its 3 H's. Next is CH2. Those H's can't be bonded to that C and something else at the same time. So this carbon, needs to be bonded to something to get to 4 bonds. If it was bonded to the H, who is then bonded to the C, that H now has 2 bonds. H's want 1 bond. So the carbons are always going to be connected to each other. Next was CH2. Then, after that, was the O, who was then connected to the other CH2, the other CH2, and the other CH3. The same thing will happen with alcohols and aldehydes. So first, what's an aldehyde? An aldehyde has somewhere at the end of this compound a C double bond O H, or the beginning of the compound. Anywhere on the left side or the right side, there's a C double bond O H. You don't have to number these, but you do need to change the ending from the E to an al for aldehyde. And since there's a double bond O, you'll always know if you have an aldehyde if you have, in the condensed formula, I'll write it over here. Let's say you were comparing this versus let me write it like this. How do you know which one's the alcohol and which one's the aldehyde? So, let's draw the top one. CH3, CH2, CH2, OH. That came out pretty easy. Let's do the bottom one. CH3, I was about to copy it. CH3, CH2, and let's say you draw it like you drew the top one. COH. That doesn't make any sense. This carbon needs 4 bonds. How can we do that? Well, this must be an aldehyde. And in fact, sometimes in the condensed formula, they might write it as HO instead to give you a hint that it's an aldehyde. I'm getting a phone call right now, and I don't want to let it go to voicemail, so I'll be right back.